Here we're going to go ahead and look at EIGRP path selection and load balancing. The first part we want to look at is the actual metric calculation. And I want to review, first, what is the calculation and how does it end up defaulting to bandwidth and delay? So I have 7 routers set up for us to kind of look at, we'll look at metrics and we'll look at K values, and then we'll look at equal cost load balancing and unequal cost load balancing. So let's go ahead and just look at one of them and review the K values there. So I pulled the console for R1 over. Let's go ahead and look at R1. Let's do a show IP protocols. I've already set up the addressing and EIGRP routing. So routing is already happening. Addressing is already there. So we want to go ahead. The routing protocol is EIGRP in Autonomous System 1. I'm using EIGRP IPv4 protocol. The metric weights, those are those K values. So when we talk about K values, we're talking about the metric weights, because remember the actual metrics being used, are bandwidth, load, reliability, delay, and then we sometimes say MTU, but that actually doesn't come and play the same way. So we look at bandwidth, load, reliability, delay. So our metric weights are these K values that we talk about. And so by default, K1 is, its weight is 1, K2 is 0, K3 is 1, K4 is 0, and K5 is 0. So let's go back to our calculation, knowing or keeping in mind that this is what our weights are by default. So when we go back, K1, what do we say? We said K1 was 1, and K2 was 0, K3 is 1, and K4 and K5 are 0. Whenever K4 and K5 are 0, then this part of the equation is set to 1. Okay, so this whole guy in here, because K4 and K5 are 0, is set to 1. What that means is we have 1 times the bandwidth plus 0 times the bandwidth, right, divided by 256, take away the load, plus 1 times the delay, times 1, because that's the value here, times 256. What happens is 1 plus, okay, we have 0 times bandwidth, anything times 0 is 0, right? So we have 1 times the bandwidth ends up just being the bandwidth. 0 times anything and then divided, it's 0 divided whatever this is, doesn't even matter because it ends up being 0, plus 1 times the delay, 1 times anything ends up being the same exact number, right? So if delay was 10, then it's 1 times 10, which still ends up being the delay of 10. So that's why I put delay there, times 1, times 256. So that's why we say by default, when we leave all the K values alone and all the weightings alone, the actual metric calculation ends up being the metric for EIGRP ends up being bandwidth plus delay. Okay? And the 256 there, the times 256 is just used for backwards compatibility with EIGRP, its predecessor. So here's the metric calculation first, and we understand that by default it's bandwidth and delay. And you can actually go ahead and change those values using the metric weights command. But you only want to do that if you really need to. We really don't want to change these K values. EIGRP works perfectly at the default values, so unless you really know what you're doing and you know that you really need to change these K values, don't do it. But if you need to do it, you can use the metric weights command. The next thing we have to take in consideration before we look at our topology is the feasibility condition. So when I can find a route using our metric calculation, we'll find the best route. If we have multiple routes to the same destination, those routes have to meet what we call the feasibility condition. The feasibility condition says that the reported distance has to be less than the feasible distance for a route to be considered a feasible successor. Okay, so a lot of times we end up using feasible distance as part of everything, and you'll even find it on some exam questions and so you're kind of, feasible distance is actually the best metric to the same destination. So if I have 3 routes to the same destination, they all have different metrics. The best one is actually our feasible distance. And so each of the next 2, if they want to be considered feasible successors, or even we'll look at that in a second. If they want to be considered feasible successors, their reported distance needs to be better than, or I'm sorry, has to be less than, or better, has to be less than the feasible distance. And I'll go through that a little bit more here. So the next part is, here's the topology we're working with. Don't worry too much about the numbers. I'll go back to it again. I just wanted you to know the IP addressing, so as we start looking at routes and things like that, you'll be like, okay, that makes some sense, right? So let's first look at our feasibility condition and what ends up becoming our successors and our feasible successors. So let's say first that this link here between R1 and R2 has a distance of 100. And we'll say that the distance here is 50. I'm just throwing out numbers right now, honestly. And the distance in here. So what we're trying to do is find the best routes and see if there are any feasible successors to get from R1 to this network here. And we'll say in here, this is 10. Okay, so this distance is 10 to get to here. Because that we'll use this 10 for each of these lengths. So then we go ahead and we say, okay, between R1 and R3, the distance is 100 again. And then between R3 and R6, this link is going to be 100. If we go down here in R1, let's say this one's 100. And we'll say the link between the distance is R4 and between R4 and R5 is 50. And we'll put another 100 here. Okay. So reported distance, so over here, we want to find out what are the reported distances to this guy. So let's calculate that first. Reported distance through R2, reported distance through R3. I've had this strange feeling I'm going to run out of little white space here, but we'll see. And reported distance through R4. R2 is going to report a distance of 50 plus this 10 down here. So he's going to report a distance of 60. R3 is going to report a distance of 100 plus this 10 right here. Okay. Then if we go through R4, R4 is going to report a distance to this 10660 network as 50 plus 100 plus this 10. So he's going to report a distance of 160. It's what, just to be clear, and I know I've said it in other segments, but reported distance is what my neighbor is telling me, is what the distance my neighbor is telling me they have in order to get to the particular network I'm trying to get to. So in this case, R4 is reporting its distance to the 10660 network. It's saying, hey, my distance to 10600 is 160. Okay. Now let's find the feasible distance. Well, let's find the metric, and then remember the feasible distance is the best metric. So the full metric to get to this route then, if I go through R2, R3, and R4, ends up being whatever the reported distance is plus what it takes me to get to my neighbor. So it's 100 plus the reported distance, 160. If I go through R3, the reported distance is 110, and the feasible distance, the metric will end up plus 100. The metric going from R1 to R3 in order to get to this 10660 network will be 110 plus 100. So it'll be 210. And then if I want to go the route through R4, what does that metric end up being? It ends up being that reported distance that R4 told me it took it to get to 10660, which is 160, plus the distance from R4 to R1. So it'll be 260. Now let's see. First things first, best metric is going to be through R2. That becomes my feasible distance. So my feasible distance is 160. Do I have any feasible successors in here? Okay. Remember, in order to be a feasible successor, you have to meet the feasibility condition. The feasibility condition says that if the reported distance is less than the feasible distance, I'm a candidate, okay, to be a feasible successor. And in fact, if we look at it, the reported distance through R3 is 110, which is less than the feasible distance. So the route through R3 becomes my feasible successor. Oh, sorry. So through R3. If I look at R4, his reported distance is 160, the feasible distance is 160. They're equal, it's not less than. This guy he's nothing. He can't be a successor. Well, he's not a successor. He's not a feasible successor either. He can't be because he doesn't meet the feasibility conditions. So when we go through our calculation, our best route is through R2, right? Our feasible successor, or our next best route, is through R3. And if for some reason they both go down, actually what would happen is the EIGRP would say, okay, if the one guy goes down, if R2 goes down, R3 becomes the best route, right? If they both go down, we don't have a feasible successor anymore in our topology table. So now we've got to go ahead and say, okay, well, let's send out some queries. Holy cow, let's see if we can find a best route, or another route, sorry, any route to 1066 if they both. And so then we send out query messages, and we put the route in active, and we wait for a response. If we get no response, then we get a stuck in active route. But anyway, so that's our calculation, and that's how it'll look. Let's go ahead and see, let's look at our own topology, or the topology I've created for you, and let's see how things turn out for us. And I'm going to get rid of the ink for a minute so that you can just look at the topology. All right, so now we've looked at the topology. It's all set up. It's all running EIGRP already, as we saw with the show IP protocols command. All the addressing. So this network's the 9. We have 3 networks going out 1066, and we're going to use that still as our example for the rest of it. I haven't messed with any of the interfaces at this point, so they're all gig interfaces. Delays are all default. Bandwidth is all the same. So what happens when bandwidth and delay is the same all the way through? I shouldn't say delay is not the same all the way through. I'm sorry, if I haven't messed with the links and the delay inherent in each device is the same, then we end up actually kind of looking at hop count. And so our network's a little bit simplistic that way, because what should happen with this network with all of its defaults the way it is that both of these guys, because we go 1 and then down, 1 and then down to get to 1066, should be in the routing table. Equal cost load balancing. I'll go through it in a second. And this guy won't be. Okay. So when we look at load balancing, we look at the calculation, and our calculation will use bandwidth and delay. By default, EIGRP will go ahead and load balance or put in the routing table all the routes up to 4 by default, okay, that have equal metrics. So up to 4 equal metric paths will automatically be put into the EIGRP routing table. You can increase or decrease that using the maximum paths and then the number of paths you want to use command. And we can change it to use unequal cost metric load balancer. I'm sorry, unequal metric load balancing if I use the variance command. And I'll explain it for a second, but then we'll go back and we'll come back again. So what variance says is, as long as you're within this range, you can be put into the routing table. So let's say that I'm going to use really simplistic numbers here, because when we actually look at our tables, they'll be very large numbers. But let's say that our feasible distance is 100, and we set our variance to be 3. Then all the routes between 100 and 300 within our variance, right, can automatically be put into the routing table. So that's how we get our unequal I'm sorry, I keep saying that, unequal metric load balancing. Okay, so if our metric is 100 and our variance is 3, variance is just a multiplier. So up here we have maximum paths. That's the number of paths, okay, that can be included. Variance is simply a multiplier to say, hey, when I take the number and I multiply it, you get a range, right? You get the beginning and you get the end. All the routes within that range can be included and those paths can be used. So let's go back to our topology and let's go ahead and verify what we have going on. So I'm in R1. Remember, I have R1, and R1 has the 3 routes, or has the, routes, paths. Has the 3 paths, all the 10.6.6.0. If I do a show IP route, I see exactly what I said I would see. In order to get to 10.6.6, we ended up having we can go through 192.168.2.2 and 192.168.1.2. And again, that's this one, right, goes to 1.2, and this one goes to 2.2. Now let's go back, okay? So let's do a show. If I do a show IP EIGRP topology, I should see all our successor and feasible successor routes. So if I do a show IP EIGRP topology, well, here all I'm seeing is that I have 2 successors and that the feasible distance is 131,072. Why aren't I seeing that route through R4? I'm only seeing the one going up to R2 and up to R3. I'm not seeing the path. I shouldn't say route. I'm not seeing the path to R4. Likely it's because it doesn't meet the feasibility condition. Okay, it's part of the topology, but if it doesn't meet the feasibility condition, which says that its reported distance, right, needs to be less than the feasible distance, it's not going to show up here because it's not a feasible successor. It's not a successor and it's not a feasible successor, so it's not going to show up in the IP EIGRP topology command or in the topology tables. Let's do an up arrow, and if we go ahead and we do an all links, it's going to show us all the links inherently in the topology table. Now we actually do see that route. Okay. And in fact, what we said was true is true. It doesn't meet the feasibility condition. Its reported distance is 131,072. It's not less than the feasible distance, which is 131,072. Okay? It's the way this is set up, and it's trying to make sure that we have a loop-free topology. You know, and in fact, the way that this is configured, if you just look at the picture, we could, in fact, have a loop. So EIGRP is working the way it's supposed to work. Now we're going to mess it up just a little bit. Not a great reason to do this, except for to demonstrate, except for that we have this topology we're working with, and we want to demonstrate maximum paths and the variance multiplier, right? So I'm going to mess with it just a little bit and change things so that, in fact, we do see we'll be able to bring up different routes. But again, to be clear, the route through that third router or through R4, or I'm sorry, the path, I gotta stop using route because to me route's really in the routing table. The path through R4 doesn't show up in the show IP EIGRP topologies because it doesn't meet the feasible distance. Its reported distance, right, is not less than the feasible distance. And it obviously won't show up in the routing table because it has a worse feasible distance than the other 2 routes that are the same. So these 2 are exactly the same. Wonderful. Here's what I'm going to do to manipulate them. You don't, and again, no good rhyme or reason behind this, except for that I want to change their metrics in order to change the feasible distance for this whole network. Because once I do that, then I can go ahead and demonstrate maximum paths and variance for you. Okay? So let's do a fig T. Whoop. I'm going to change their delay. You could change delay or bandwidth, and I think either is probably fine. It depends upon your situation. Sometimes it's not a good idea to change the bandwidth because bandwidth as a measurement is used in quality of service. So some of those things, you know, an automatic discovery of things and then automatic, like auto QoS, you may have some difficulties if you go ahead and change bandwidth. So you could change delay. So if I do an int range, the two interfaces that I have on this router that they go to R2 and R3, the ones that are good networks here, the 1.2 and the 2.2. They are gig 1 and gig 2, so I'm just going to go ahead and change the delay on both of them. I'm going to change it to 30. Okay. Now let's go ahead and do a show IP route. Sorry. Now if I show an IP route, what happens is I have effectively changed the metric going on the path to R2 and R3, and our path towards R4 has become our best and only best route to get to the 10.6.6.0 network. Let's do a show IP EIGRP topology. Now the difference here, now what you'll see is that all three of those paths are in there because now all three of them meet the feasibility conditions. Effectively, by changing the delay, what I've done is changed the metric for the first two good routes that we originally had. I've changed them to 138.496, which now makes them higher than the metric going through R4, 131.328. So now the feasible distance is 131.328. And these guys are in the topology table because they are feasible successors. Because their reported distance of 138.16 is less than the feasible distance of 131.328. So these guys are feasible successors. If this guy goes down, these guys will come up automatically, right? Because that's the goal of EIGRP, to recover quickly. These two guys here have the same cost, but they have, have the same metric, but they have a worse metric than this guy. And so he is the only route with the best metric to the destination. So when we look at, you know, if we go back up to our show IP route, there's only one route here, whereas before there was two because there were two good routes, equal metric routes that were the best routes to get to the destination. So I could put two in there, right? By default, I can put 4. This guy has the best metric. These guys don't have the best metric, so we only have one route that has an equal metric. You know, if there was another route with a 131.328, sorry, this would work. We would have multiple paths to the destination, but now we only have one. So let's go ahead and demonstrate unequal metric load balancing, or unequal metric routes being put in the routing table. We'll use the variance command. And all it is variance and, whoops, and the number you want to use. Honestly, I don't have to use a very big number here. I can't use 1 because one's the default. 1 specifies that we can only use equal metric paths. I don't want to do that. You can see, though, that the difference between them isn't that big. Right, so I could do a variance of 2, and it should bring up these other paths and bring them into the routing table. So variance of 2. So what that means is 131.328 times 2. I can have anything between here and whatever that number is of 131.262, right around 263, right? So between the 131 and the 263, about. If the feasible distance was that, those routes would be put in the routing table. Now these ones are pretty close, so they should be in there already. Let's do a do show IP route. And in fact, now they're all in there. So we've demonstrated that that works. So we've looked at the topology table, we've discussed the calculation, we've discussed the feasibility condition. One last thing, we'll just do maximum paths. Now, maybe I would generally want to increase the number of paths that I could, but I just want to show you that the command can be used within the topology we have, and it's just a little bit easier. Instead of building a ginormous topology, to just go with less paths. So right now we have 3 paths to our destination, right? We can go through 03, 02, or 01. Even though these two, their metric is greater than this metric, because they're within that variance that we set, they get put in the routing table. Now we're still in EIGRP routing, as signified by config router. So let's go ahead and do maximum paths. I shouldn't try to type it all off. You can just do path completion as tab completion, as you guys, I'm sure you all know by now. I tend to just kind of type it out for you, but I should really stop because I can't spell anyway. Let's say our maximum paths are 2, so we want to just have 2 paths in our routing table. So we'll do maximum paths of 2. And now we'll do a show IP route. Sorry. Uh-oh. Oh, we're good. Whew. I saw this one lined up and it messed with me for a second. Now, in order to get to 10.6.6, it's only going to use these 2 paths. And only because I set maximum paths. Right? If I go back to the default, or if I go to maximum paths of 3, all 3 of them will show up. Well, I think that was it. I think that was all I wanted to cover with you. Hope I remembered everything. So let's just do a quick review. Let's erase all our ink real quick. Now, originally, when we left everything in its default, these guys were our best path, right? And this guy didn't even show up because he didn't meet the feasibility condition. So this, going this way, didn't even show up in our routing table or our topology table because he couldn't be a feasible successor. He didn't meet the feasibility condition, which says, right, which says my reported distance needs to be less than my feasible distance. In fact, they were equal, so this guy didn't show up. Then we went ahead and we changed the delay. We added a delay of 30, which actually then made this guy the better route because these aren't equal. These 2 guys weren't equal to him. We changed the way we went, and our routing table ended up going, or our route, in our routing table, this was the only route, and this was the only way to get to this network. Then we configured, so because equal cost load balancing by default, right, or equal metric load balancing by default. Because this metric became greater than this metric, this guy was the only one. Then we configured a variance of 2, which said as long as you're within this feasible distance times 2, it's fine. Or the best route metric, if you want to call it that. Then go ahead and you can be included. So then at that point, we did unequal metric load balancing, and all 3 of these showed up. And then we went ahead and we configured max paths to 2. And then that meant that only like 2 of these showed up. So that's it. If you have any questions, let me know.